Woven fabric consists of threads intertwined in the warp and weft directions. Woven fabrics made from non-stretchy yarns exhibit resistance to stretching along the yarn directions. However, they allow shearing in the diagonal directions. Here is an example of deforming a piece of silk fabric. While the yarns themselves are not stretchy, the fabric admits significant deformation due to shearing. We are interested in geometrically modeling the shearing deformation in the woven fabric. Fabric is commonly modeled as a developable surface using isometric parameterization, implicitly assuming that the fabric behaves similarly to a sheet of paper, which is inextensible in all directions and incapable of shearing. We therefore need a different model for woven fabric that permits shearing. The great mathematician, Chebyshev, has proposed a geometry solution to model woven fabric, which nowadays is called a Chebyshev net. This is a surface parameterization function that preserves length along the parametric lines. Mathematically, the surface parameterization should ensure that the gradient with respect to u and v coordinates has a length of 1. If we consider the u and v parametric lines as the weft and warp yarns, these constraints imply that the lengths along the yarn directions are preserved. In the world of discrete geometry, we are usually given as input with a 3D triangle mesh without UV coordinates. Therefore, our objective is to solve for a flattening function such that its inverse is a Chebyshev net. We call it a Chebyshev flattening function. This task is challenging since the constraints on the inverse mapping include unknown yarn directions, namely the UV coordinates that need to be solved. Our formulation is based on the Jacobian of the parameterization f. For a Chebyshev net, its Jacobian describes how a square is deformed into a diamond shape, where the edge length is preserved. We can take a closer look at the Jacobian by applying singular value decomposition. The V matrix first rotates the square by 45 degrees, which aligns its diagonals with the coordinate axis. The sigma matrix then stretches along the coordinate axis while maintaining the original edge length. The two singular values should be constrained to ensure the edge length is preserved. This results in a diamond shape. Finally, the U matrix rotates the diamond shape to align it with the yarn directions in the deformed configuration. Recall that our goal is to solve for a flattening function g such that its inverse is a Chebyshev net. This implies that the Jacobian of G inverse should have the form we just discussed. Equivalently, we can say that the Jacobian of the flattening function G should have the derived form with inverse rotation and singular values. The collection of all matrices in this form defines our search space. We can then measure the distance between the Jacobian of flattening function G and the search space based on the matrix Frobenius norm. Minimizing this distance would lead us to the expected Chebyshev flattening. We adopt a local global approach to solve this problem. In the local step, we look for the closest projection within the search space with a given Jacobian. In the global step, we solve for the flattening function g such that its Jacobians are as close to the projections as possible. We then repeat these two steps until convergence. We initialize our method with a conformal map, and compare the results to a recent baseline with the same initialization. For simple shapes, both of the approaches produce reasonable results with low Chebyshev net error. However, more complicated meshes demonstrate the robustness of our method, which produces more accurate results and is less likely to fail due to numerical instabilities. We can extract a Chebyshev net from our computed Chebyshev parameterization, which is a popular application in architectural design. Our formulation also supports computing deformations of flat sheets, where the input warp and weft directions are constrained to remain a Chebyshev net. Here we show a real-time deformation of a cylinder shape, where we apply translation and scaling to the selected handles. This enables various applications in woven fabric manipulation, including interactive draping. Please see our paper for more details.